In this video, we're going to see typical parameters that characterize undrained loading. And we will start by looking at what is the pressure that we would expect due to loading under undrained conditions in a porous solid. All right, so we will start by recalling the diffusivity equation. And here in the diffusivity equation, if I assume undrained conditions in which nothing gets in or gets out from the solid, then I can get rid of this term, and also I can get rid of the time. Basically, I'm not considering that things are changing here with time. So I can write by rewriting this equation that the change of pressure due to a change in volumetric strain under undrained conditions, in which the mathematical expression for undrained condition is that there is no change of fluid in the pore space. This is going to be equal, just from here, to negative alpha times the Biot modulus, where the Biot modulus, if you remember, it is equal to the Biot coefficient minus the initial porosity divided the matrix of the modulus of the matrix, and here porosity divided the bulk modulus of the fluid, and all of these inverse. So this product then is going to tell me what is the proportionality parameter between pressure and volumetric strain, so that, for example, if I wanted to compute what is the expected change of pressure due to a change in volumetric strain, then the proportionality parameter is negative alpha times the Biot modulus. Notice that in the conventional mechanics notation, a contraction is going to be a negative strain, and the compression that causes that contraction, negative to negative, is going to be positive, so that's going to be an increase of fluid pressure. Okay, so let's try to get a sense of more or less what would be this increase of pressure for some parameters that I have chosen here for a tight sandstone. So let me bring into the screen this spreadsheet in which I have taken representative parameters for a tight sandstone that we wrote a paper recently. And let me bring all this into the picture too. I'll share the links for the paper in the description of the video. So here we have a study of a tight sandstone in which you can see the bulk density as a function of porosity. And here I have taken one with about 5% porosity, for which we measure static modulus and Poisson ratio, and also static dynamic modulus and Poisson ratio. But more or less from here, I chose one of these values for which the porosity connected is about 5%. The Young modulus is about 5 million psi or 34 gigapascal. This is the Young modulus. This is what we measure. Poisson ratio, it's about 0.15. And also, by getting to know the mineralogy of the rock and using an average between the Royce and Boyd moduli, we can get also the modulus of the matrix, which is about 35 gigapascals. So with this data, what I did is with the equation of isotropic elasticity, I calculate the bulk modulus based on the Young modulus and the Poisson ratio measured on the dry rock. And from here, and knowing also what is the modulus of the matrix, we can calculate what is the BO coefficient alpha. And in this case, it's about 0.53. Remember, this is a tight sandstone. The modulus is actually is very high. So just to play a little bit, let me change this to, for example, a fifth of the Young modulus. So you see right away that the BO coefficient increases significantly. All right, but let me take it back to the actual value, which was 5 million psi. All right, so for these typical values, I calculated the BO modulus and alpha times the BO modulus, which is this proportionality parameter that we have over here, considering cases in which the fluid within the porous solid it's made out of a mixture of gas and liquid, with gas that has a very high compressibility, and actually that bulk modulus it's a very small number, and for the fluid I assume they have a low compressibility with a bulk modulus of 2.2 gigapascals. So here using the Roy's lower bound for that bulk modulus, I get the bulk modulus of the fluid, which is also is going to be a mixture. And what we see very clearly is that the bulk modulus of the fluid increases significantly as we approach the liquid of fraction close to 1. But even if you have a small fraction of gas or bubbles, like for example, just 1% of bubbles or 1,000 of a bubble will affect significantly the bulk modulus of the fluid as a mixture, as a bubbly mixture. And just when we get with the liquid fraction equal to 1 is that we recover the bulk modulus, in this case of water. So what I did is I calculated the BL modulus for that, which in this case, we can see the result. Let me here zoom out a little bit. One more. Okay, so one more. The BL modulus increases significantly with the percentage of the liquid fraction. I forgot to correct this. This is actually the liquid fraction, and just when it gets close to 1, we have a high value of the BL modulus. And here I also have alpha times the BL modulus, which is the parameter that we saw that was important to characterize here the increase of pressure. And I want to leave it further and assume that I had a volumetric strain of 1/10,000 or 1/10,000, or I could say also 0.1 thousandths of a strain. So this is a very small strain, but even with that very small strain, according to the equation that we obtained, in which the change of pressure dP is going to be proportional to the product of these two, we get that the change of pressure expected it's relatively small when the fluid has a significant amount of gas and increases as the gas starts to decrease, and therefore the change of pressure increases. So here, for example, for a fluid, for this porous rock filled with water, if we had such a strain and we strain this under undrained conditions, the change of pressure will be 1.46 megapascal. And this is a relatively large number. This is higher than 200 psi, something that you can definitely measure if you were to have such undrained loading. So the changes of pressure during that undrained loading are not insignificant. And in this example, you can see what the value would be if you had such process. Okay, so this is the first parameter, alpha times the BL modulus. The second parameter that is also interesting to know and to characterize is what is called as the undrained bulk modulus. So far, when we referred to the bulk modulus of a porous solid, we were using, sometimes without knowing, the drained bulk modulus or the dry bulk modulus, in which the dry bulk modulus or drain bulk modulus is the change of mean stress that I need per unit of change of volumetric strain in order to cause such deformation. So these, either under drained conditions or with a dry rock with a fluid that has a very large compressibility, this results in the bulk modulus K, and we usually just denote that with K and nothing else. But remember that this is the bulk modulus of the porous solid drained or dry. And this is, for example, the one that I estimated in this example that I was mentioning before, in which we measured the Young modulus under dry conditions and also the Poisson ratio, and with that we could get also the bulk modulus in dry conditions. But in this case, then, as the name indicates, we're not taking into account undrained loading. So what would happen if we were to load the rock, increase stress in all directions, cause an increase in volumetric strain, but now to do this under undrained conditions? The result of that is not going to be equal to the previous one in the general case, and it is what is called undefined as undrained loading, or in this case undrained bulk modulus, KU. Alright, so what is this undrained bulk modulus and how can we calculate that? In order to do that, we're just going to use the equation that we derived in one of the first lecture, one of the basic equations of pore elasticity, that tells me that the total mean stress is proportional to the bulk drain modulus times the volumetric strain minus the BO coefficient times the pore pressure. So if I take a derivative of this total stress with respect to the volumetric strain, what I get is K minus alpha, and probably, as we said, the pressure is going to change during this undrained loading, so I need to quantify that change of pressure. Remember that K and alpha are constants. So from here, what I can do is I can extend this now for undrained loading. So for undrained loading, and let me extend this arrow. No, this is going to be okay. So if I were to now extend this equation to the case of undrained loading, where this is the condition for undrained loading, this is going to be equal to K minus alpha, and the change of pressure due to change of volumetric strain is actually what I obtained before, what I obtained in the previous equation. So it's just going to be alpha times the BO modulus. So then this derivative is just going to be negative alpha times the BO modulus. And as a result, this undrained bulk modulus, by definition, KU, is going to be the bulk drain modulus times alpha squared times the BL modulus. And this is the undrained bulk modulus. And notice that it is going to be higher than the drain bulk modulus because now we're taking into account also the stiffness of the fluid within the pore space, which is taken into account through this BL modulus, where the BL modulus depends on the poroelastic parameters, alpha, initial porosity, bulk modulus of the matrix, but also on the bulk modulus of the fluid. All right, so let's see an example of for what of these undrained bulk modulus look like. And for that, let me bring again this spreadsheet over here, where we have now the undrained bulk modulus as a function of the liquid fraction. And what we see mostly in this graph is that when we have some bubbles, even if the quantity is very small, the undrained bulk modulus gets pretty close to the value of the drained bulk modulus, which is over here, 16.4. And you see this undrained bulk modulus here is 16.7, so very close because still the fluid is quite compressible. But once I get into a condition in which the fluid is completely filled with water with a modulus of now 2.2 gigapascals, then the undrained bulk modulus increases to the value of 24.15 gigapascals. So we see very clearly here that for the same sandstone, depending on what the fluid is made of, the undrained bulk modulus can increase quite a bit. And the last parameter that we're going to see that characterizes the undrained loading process is what is called the Skempton parameter. For the Skempton parameter, we're going to use the letter B, and B, or Skempton parameter, is going to be defined as -1 times the change of pressure expected due to a change in mean stress, total mean stress, under undrained conditions. Let me see if I used the F before. Yeah, I did use the F over there. So density of the fluid times porosity equal to 0. All right, this is what we define as the Skempton parameter. And let's see what that Skempton parameter looks like. Okay, well, before I do the definition, actually, let me explain what is a practical application of this Skempton parameter. As we have seen in these plots, the undrained bulk modulus changes significantly as we approach 100% saturation of a fluid with water. And let me change also this over here. This is going to be also the liquid fraction. And we use the Skempton parameter in order to tell if a sample has reached total saturation or not. Because when it's far from full saturation, that impacts significantly on the undrained bulk modulus and also on the P wave velocity that we measure in such a sample. So if, for example, we wanted to do a test and especially an undrained test, or measure a P wave in a fully saturated rock or sediment, before doing that, we use the Skempton parameter, and basically what is done is to subject a sample to undrained loading, or at least try to subject it to undrained loading. So imagine that here we have a port so fluid can communicate with the fluid within the sample, and here we have a pressure gauge. So what we're going to do in this kind of test is to apply a stress and specifically change of stress through a membrane. Let me delete this line. I'm going to redraw this again. But here we have a membrane that goes around the rock, so we don't have communication between the confining fluid and the pore fluid. And we apply this change of mean stress in order to measure a change of pore pressure in the pore space. And this is exactly what you have in this equation, and whether this change of pore pressure is comparable to the change of mean stress, that's going to tell me if the rock is saturated or not. And that's basically the Skempton parameter. Okay, so let's go then to the equations in order to calculate what this Skempton parameter is as a function of the other poroelastic parameters. So in order to do that, we'll start with the first equation of pore elasticity. And here, what we're going to do is to take the derivative of the total stress with respect to pressure. This is going to be, K is going to be a constant. The sample is going to change in size, so this deformation, I need to consider its variation with a change of pressure, and the derivative of P with respect to P is just going to be 1, so this is just alpha. And from here, I'm also going to use what I used before, which is the change of pressure due to a change in volumetric strain from the first characterization that we did, and we saw that this was proportional to negative alpha times the BO modulus, and in this case, since this is the inverse of the derivative that we had before, then also this is the inverse here, and this times alpha, and finally, by definition, the the Skempton parameter B is going to be equal, just working with these equations, it's going to be equal to, I'm going to take a common factor 1 over alpha, and this is going to be K times M plus alpha squared. Notice in the definition over here we have a negative sign, so that's why these have changed sign. This is the value of the Skempton parameter as a function of the other poroelastic parameters. So as I mentioned before, this Skempton parameter, it is important in order to get to know if a sample is fully saturated, and in order to do an undrained loading if needed, and also in order to get to know if the sample is fully saturated, so the P wave that we measure is the one that corresponds to the P wave in fully saturated conditions. This is something which is overlooked sometimes, but it is extremely important when you compare P waves measured in the field and P waves measured in the laboratory. Because in the laboratory, many times, we don't do such a great job saturating rocks, and therefore the P waves that we measure in the laboratory are lower than the P waves that we have in the field under fully saturated conditions. And let me just close by looking again at this plot where we have the Skempton coefficient as a function of the liquid fraction, and you can see that even if you had a 1% of volume fraction of bubbles within your rock or sediment sample, your Skempton parameter is going to be very low, and your undrained modulus is also going to be lower than what you would expect under fully saturated conditions here with water, and also the expected P wave velocity will be quite different even if you have a 1% saturation of the fluid with bubbles.